Welcome to Pre-Calculus. Today we will investigate finding partial fraction decompositions of rational expressions. We'll take a look at two examples. The first example is rational expression negative 6x minus 22 over x squared plus 2x minus 3. My goal is to write this somewhat complicated rational expression as the sum of multiple simpler ones. And the way that I decide how many fractions that I want to split this up into depends on the denominator. And it really has to do with how x squared plus 2x minus 3 factors. So the first thing I want to do is I want to factor the denominator. So I'm going to write negative 6x minus 22 over x squared plus 2x minus 3 is going to factor as x plus 3 times x minus 1. So we're trying to multiply to negative 3. So 3 times negative 1 does that. And add up to positive 2. 3 plus negative 1 is positive 2. So that checks out for us. And once I find those factors, that tells me that I need to make this partial decomposition into two fractions. One with a numerator over x plus 3. I'm going to call that numerator a sub 1. And then a second fraction added to it, a sub 2. Again, I don't know what that is yet, over x minus 1. Now my goal, once I figure out how many fractions to divide this rational expression into, is figure out what's my a sub 1, my a sub 2, what are my numerators. And the way that we do that is we imagine that we're going back from this sum of two fractions back to the single fraction. And to do that, I would need to make the denominators the same. So I would multiply by x minus 1 above and below on this first fraction to get that common denominator. And on the second fraction, I'm missing the x plus 3 factor. So I would include x plus 3 multiplied above and below. And what I want to do now is I want to create an equation where I set my numerators equal. So I'm going to record this down below. It's negative 6x minus 22, the original numerator, should equal whatever a sub 1 is times x minus 1 plus whatever a sub 2 is times x plus 3. Now, I need to choose some specific x values, and the way I'm going to choose them is based on these factors. So as I look at this first one, x minus 1, I'm going to choose an x value that will cause that to reduce to 0. And my goal there is to let a sub 1 zero out so that I can solve for a sub 2. So my first x value I'm going to choose is x equals positive 1. So I'm going to substitute x equals 1 into everything. So I'll just leave gaps here. I'll put that in the blue in a moment. So a sub 1 times gap minus 1 plus a sub 2 times gap plus 3. And I'll put a 1 in all those gaps. And just like we predicted, this 1 minus 1 is going to reduce to 0 times a sub 1 is going to be 0. That whole term is going to fall out. So what I've got now is negative 6 times 1 minus 22. That's negative 28 equals a sub 2 times 1 plus 3, or 4. And that I can divide by 4 to solve for a sub 2. And immediately I see a sub 2 has the value of negative 7. So when I go back to fill in, I'm just going to note that a sub 2 is going to be negative 7. In fact, we can start writing our partial sums here. So it's going to be negative 7 over x minus 1. So when I take stock, what I need to complete now is a solution for a sub 1. If I get that, then I'm complete. I'm done. So we want to use a similar strategy. I had used x equals 1 first. Now I need to turn my attention to the other binomial, which is x plus 3. And I want to choose an x value. When I substitute it in x plus 3, will create a 0 and cause a sub 2 to 0 out. So it looks like negative 3 would be a good choice there. So I'm going to put x equals negative 3. And just like we did for x equals 1, I'm going to substitute negative 3 for x wherever it occurs. So I'll list it out first with gaps, and then I'll fill in with negative 3 plus a sub 2 times gap plus 3. And now we'll substitute negative 3, negative 3, and negative 3. And that last one, again, is going to 0. a2 times 0 is 0. That whole term drops out. So now I want to solve for a sub 1. So negative 6 times negative 3 is positive 18 minus 22 is negative 4. Is going to equal a sub 1 times negative 3 minus 1 is also negative 4. When I divide there, I see that a sub 1 is just 1. And that completes my partial decomposed fraction. Notice it's much, much simpler than the original negative 6x minus 22 over x squared plus 2x minus 3. Let's take a look at a second example. So this second example has negative 72 minus 11x over x cubed plus 3x squared minus 10x minus 24. And the first thing I notice is that the denominator is a degree 3 polynomial taken out all the way to the constant. So I need to factor that, but like we've seen as in our investigations in past lessons, I can't just factor directly. I need to use the rational root theorem to come up with an initial factor, and then I can use the factoring of the quadratic. So I'm going to start by just noting what my p and q values are for this denominator polynomial. So I'm going to start with that negative 24, and I'm going to list out factors. There's a lot of factors to 24. So I'm going to start with 1. Plus or minus 1 would divide 24. Plus or minus 2 would divide 24. Plus or minus 3. Plus or minus 4. Plus or minus 6. Plus or minus 12. And plus or minus 24 itself. So a lot of factors in 24. My q values are not so numerous. I just have a 1 coefficient out front. My leading coefficient's 1. So there's not a whole lot of variety here. Q is either positive or negative 1. So when I list out my possible roots, p divided by q, it really is this list of p values because q is just 1. So these are the ones I'm going to check with synthetic division. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12, plus or minus 24. So I don't want to check all of those. I hope I find a rational root at the beginning of the list. But let's run the division. So I'm going to write here my first value. I'm going to choose plus 1. Typically I start there with the smallest values just to see if they're roots. And then I'm going to list out the coefficients of the denominator. So it's 1x cubed plus 3x squared minus 10x minus 24. It's real important to get those correct. The process works, but everything has to be very accurate. So I'm going to start with the division process. I'll carry down that first 1, and then I'm going to multiply. 1 times 1 is 1. And then I'll add 3 plus 1 is 4. Now I'll multiply again. 1 times 4 is 4. Negative 10 plus 4 is negative 6. 1 times negative 6 is negative 6. So that didn't work. I need a 0 there at the end. So I'm just going to start again. And I'll try negative 1 now. If the positive didn't work, we'll see if the negative does. So again, I'm going to start with negative 1 times 1 is negative 1. 3 plus negative 1 is 2. Negative 1 times 2 is negative 2. Negative 10 plus negative 2 is negative 12. Negative 1 times negative 12 is 12. and negative 24 plus 12 is negative 12. So again, that one didn't work either. Let's try with 2. So we exhausted the ones, and this highlights that this is really a possible list of rational zeros. There is guesswork involved. So let's see if we can find one. 2 times 1 is 2. 3 plus 2 is 5. 2 times 5 is 10. Negative 10 plus 10 is 0. 2 times 0 is 0. And that adds to negative 24. So that, again, didn't enter our list of rational zeros. So what we'll try now is negative 10. I'm sorry, negative 2. And run the process a third time. So now negative 2 times 1 is negative 2. 3 plus negative 2 is 1. Negative 2 times 1 is negative 2. That's negative 12. Negative 2 times negative 12 is positive 24. And lo and behold, eureka, we found it. One of my factors here is x plus 2. So I'm going to start writing here that one of my fractions needs to be a sub 1 over x plus 2. So remember, if I've found the divisor is negative 2, we switch the sign for the factor. So what's left is the quadratic 1x squared plus 1x minus 12, and I need to factor that. So once you've found one of these factors with synthetic division, I can factor directly once I've reached the quadratic. So I'm trying to multiply to negative 12 and add up to positive 1. So that's going to be x plus 4 times x minus 3. And that gives me the rest of my fractions here for the partial sum. So it's a sub 1 over x plus 2 plus a sub 2 over x plus 4 plus a sub 3 over x minus 3. And that's my list. So at that point, I want to then use my same strategy that I came up with in the first example to set up a numerator equation that I can substitute values in and out of. So I'm going to note, because I got 3 of these for my common denominator, I have to have 3 factors total. So this first one's going to be multiplied times x plus 4 times x minus 3 above and below. The second one's missing x plus 2 times x minus 3 and the third one is missing x plus 2 times x plus 4. And again, what we're doing is we're imagining that we're going the reverse direction, taking this back to the single fraction. But now what I want to do is use the strategy of setting the numerators equal. So now what I'm going to record is negative 72 minus 11x equals a sub 1 times x plus 4 times x minus 3 plus a sub 2 times x plus 2 times x minus 3 plus a sub 3 times x plus 2 times x plus 4. So it's a bigger equation because I had a larger denominator polynomial. It's x cubed instead of x squared. So the first number that I'm going to choose is going to really zero out 2 of these. And where I'm going to look, we could choose any number of these factors to zero out, but I'm going to choose x plus 4. So I see that it's in 2 of these products. It's in the first and the third. And so when I choose negative 4, x equals negative 4, I'm consciously trying to zero those out. So let's write it with negative 4 substituted in. So we got negative 72 minus 11. I'll leave a gap there. We'll put the negative 4 equals a sub 1. I'll leave a gap in all these places where we got x plus a sub 2. And then plus a sub 3. And we're ready to substitute in our minus 4 for x. And again, what we're looking for are some cancellations. So right away on this first one, I see negative 4 plus 4 is 0, which is going to zero out that whole product. We'll come back to the a sub 2 term because that will not zero out. We'll see how that works. But a sub 3, because of this negative 4 plus 4, will zero, and that whole last product will zero out. So now what I've got is negative 72 minus 11 times negative 4. So that's negative 72 plus 44. And we'll just subtract that. So it looks like that's going to be negative 28 equals, that whole first term is 0. And then my second term is going to be a sub 2 times negative 4 plus 2 is negative 2 times negative 4 minus 3 is negative 7. And then the third term will also zero out. So negative 2 times negative 7, that's a sub 2 times 14. So all I got to do is divide by 14. And I see right away that a sub 2 is going to be equal to negative 2. So we found one of the numerators. Now I need to find the other two. So again, I'm going to choose an x value that's going to allow me to zero out two of the other numerators. So while we've been focusing on the negative 4 to cancel the first and the third, we'll now see if we can cancel the middle one. So I got to rewrite those, and let's see what x value we should choose now. So we found a sub 2, so it looks like if I were to choose something that would cancel out this binomial x plus 2 in the second and third, then I could capture a sub 1. So my second value I'm going to choose for x is negative 2. So again, I'm going to set it up, negative 72 minus 11. Put a negative 2 there in a moment. So a sub 1 blank plus 4 blank minus 3 plus a sub 2 blank plus 2 times blank minus 3, and then plus a sub 3 blank plus 2 blank plus 4. So all those blanks are going to be negative 2's because I substituted in negative 2 for x. And just like in our first run through with x equals negative 4, here I'm going to get some zeros, so that whole second product will zero out, as will the third. So when I go to solve here for a sub 1, again, I'm going to get negative 72 times negative 11 times negative 2. So that's negative 72 plus 22, which is going to give us negative 50 equals a sub 1 times negative 2 plus 4 is 2 times negative 2 minus 3 is negative 5 plus 0 plus 0. So again, all I need to do is multiply. This is going to be a sub 1 times negative 10. And all I've got to do to solve is divide by negative 10. And we see that a sub 1 is negative 50 divided by negative 10, or 5. So that solves for two of those. All that's left is the third numerator, which is a sub 3. So again, I'm going to change my view here. We'll get these written back on the original equation. Now what I want to do is I want to leave a sub 3, but I want to get rid of a sub 1 and a sub 2. So the common factor there is x minus 3. So I'm going to choose an x value so that x minus 3 becomes 0. And you got it. It's going to be x equals 3. So just as we did with the first two, I'm going to substitute for x 3. So negative 72 minus 11 times blank, that'll be a 3, equals a sub 1 times blank plus 4 times blank minus 3 plus a sub 2 times blank plus 2 blank minus 3 plus a sub 3 blank plus 2 blank plus 4. And we're substituting in positive 3 here for x. So for that first term, I got a 3 minus 3. That's a 0 times these things will make another 0. Same for this a sub 2 product, becomes 0. And all we're left with is a sub 3. So that way that this is going to simplify will be negative 72 minus 11 times 3. So that's negative 72 minus 33, which is going to be negative 105, equals 0 plus 0 plus a sub 3 times 5 times 12. I'm sorry, not 12, 7. So it looks like that's going to be a sub 3 times 35. So all I've got to do is divide both sides by 35. And that will help me solve for a sub 3. So 35 times 3 is 105. So it looks like our value for a sub 3 is going to be negative 3. Once I've got all three of those, I'm ready to write my partial fraction decomposition. So I'm going to write this up above, just since that's where I've got room here. So it's going to be a sub 1, which we solved to be 5, over x plus 2, plus a sub 2, which we calculated to be negative 2, over x plus 4. And lastly, plus a sub 3, which is negative 3, over x minus 3. And that completes that decomposition of the original rational expression into a sum of 3 much simpler ratios. And this task really will come in useful in calculus when you're integrating rational expressions. It just makes it easier. Thank you for joining for this investigation of decomposing rational expressions into partial fraction sums. See you soon.